Chapter 5, the Periodic Law, Section 2, Electron Configuration and the Periodic Table. After this video, I want you to be able to explain the relationship between electrons and sublevels and the length of each period of the periodic table, locate and name the 4 blocks of the periodic table and explain the reasons for these names, discuss the relationship between group configurations and group numbers, and describe the locations in the periodic table and the general properties of alkali metals, alkaline earth metals, the halogens, and the noble gases. The group 18 elements of the periodic table, the noble gases, undergo few chemical reactions. This stability results from the gases' special electron configurations. Helium's highest occupied level, the 1s orbital, is completely filled with electrons, and the highest occupied levels of the other noble gases contain stable octets. Generally, the electron configuration of an atom's highest occupied energy level governs the atom's chemical properties. Periods and blocks of the periodic table. While the elements are arranged vertically in the periodic table in groups that share similar chemical properties, they are also organized horizontally in rows or periods. As can be seen in Table 5-1 on the screen or on page 128 of your text, the length of each period is determined by the number of electrons that can occupy the sublevels being filled in that period. In the first period, the 1s sublevel is being filled. The 1s sublevel can hold a total of 2 electrons. Therefore, the first period consists of 2 elements, hydrogen and helium. In the second period, the 2s sublevel, which can hold 2 electrons, and the 2p sublevel, which can hold 6 electrons, are being filled. Consequently, the second period holds 8 elements. Similarly, the filling of the 3s and 3p sublevels accounts for the 8 elements of the third period. Filling 3d and 4d sublevels in addition to the s and p sublevels adds 10 elements to both the fourth and fifth periods. Therefore, each of these periods total 18 elements. Filling 4f sublevels in addition to s, p, and d sublevels adds 14 elements to the sixth period, which totals 32 elements. And as new elements are created, the 23 known elements of period 7 could, in theory, be extended to 32. The period of an element can be determined from the element's electron configuration. For example, arsenic, As, has the electron configuration argon 3d10, 4s2, 4p3. The 4 in the 4p3 indicates that arsenic's highest occupied energy level is the fourth energy level. Arsenic is therefore in the fourth period in the periodic table. The period and electron configuration of each element can be found in the periodic table, which is found on the back cover and on pages 130 and 131. Based on the electron configurations of the elements, the periodic table can be divided into 4 blocks: the S, P, D, and F blocks. This division is illustrated in figure 5-5 on the screen right now, or on page 129 of your text. The name of each block is determined by whether the S, P, D, or F sublevel is being filled in successive elements in that block. The S block elements, groups 1 and 2. The elements of the S block are chemically reactive metals. The group 1 metals are more reactive than those of group 2. The outermost energy level in an atom of each group 1 element contains a single s electron. For example, the configurations of lithium and sodium are helium 2s1 and neon 3s1 respectively. As you will learn in the next section, chapter 5, section 3, the ease with which the single electron is lost helps make the group 1 metals extremely reactive. Using N for the number of the highest occupied energy level, the outer or group configurations of the group 1 and group 2 elements are written NS1 and NS2 respectively. The elements of group 1 of the periodic table, lithium, sodium, potassium, rubidium, cesium, and francium, are known as the alkali metals. In their pure state, all of the alkali metals have a silvery appearance and are soft enough to cut with a knife. However, because they are so reactive, alkali metals are not found in nature as free elements. They combine vigorously with most nonmetals. and they react strongly with water to produce hydrogen gas and aqueous solutions of substances known as alkalis. Because of their extreme reactivity with air and moisture, alkali metals are usually stored in kerosene. Proceeding down the column, the elements of group 1 melt at successively lower temperatures. With the exception of lithium, the alkali metals have melting points lower than the boiling point of water. Lithium, Li, sodium, Na, and potassium, K, are less dense than water. The elements of group 2 of the periodic table, beryllium, magnesium, calcium, strontium, barium, and radium, are called the alkaline earth metals. Atoms of alkaline earth metals contain a pair of electrons in the outermost s sublevel. Consequently, the group configuration for group 2 is Ns2. The group 2 metals are harder, denser, and stronger than alkali metals. They also have higher melting points. Although they are less reactive than alkali metals, the alkaline earth metals are also too reactive to be found in nature as free elements. Here we see figure 5-4 from page 132 of your text, showing potassium reacting very strongly with water and needing to be stored in kerosene. Here we also see from figure 5-8, calcium, an alkali metal, is too reactive to be found in nature in its pure state. So instead, it exists in compounds, like in minerals or making up marble, as we see on the right. Hydrogen and helium. Before discussing the other blocks of the periodic table, let's consider two special cases in the classification of elements, hydrogen and helium. Hydrogen has an electron configuration of 1s1, but despite its ns1 configuration, it does not share the same properties of the elements of group 1. Although it is located above the group 1 elements in many periodic tables, hydrogen is a unique element with properties that do not closely resemble those of any group. Like the group 2 elements, helium has an ns2 group configuration, yet it is part of group 18. Because its highest occupied energy level is filled by 2 electrons, helium possesses a special chemical stability, exhibiting the unreactive nature of the group 18 elements. By contrast, the group 2 metals have no special stability. Their highest occupied energy levels are not filled because each metal has an empty available p sublevel. The D block elements, groups 3 through 12. In the D block elements, groups 3 through 12, filling the Ns sublevel is followed by the addition of the electrons to the D sublevel of the preceding, or N-1, energy level, as we see represented by figure 5-9 on the screen right now, or on page 134 of your text. In addition to the 2 Ns electrons of group 2, atoms of the group 3 elements each have 1 electron in the D sublevel of the N-1 energy level. The group configuration of group 3 is therefore N-1 D1 Ns2. 9 more electrons are added to the D sublevel across each period. Atoms of the group 12 elements have 10 electrons in the D sublevel plus 2 electrons in the Ns sublevel. The group configuration for group 12 is N-1 D10 and Ns2. As you read in chapter 4, some deviations from the orderly D sublevel filling occur in groups 4 through 11. As a result, elements in these D block groups, unlike those in S block and P block groups, do not necessarily have identical outer electron configurations. For example, in group 10, nickel has an electron configuration of argon 3d8 4s2. Palladium, Pd, has a configuration of krypton 4d10 5s0. And platinum, Pt, has the configuration xenon 4f14 5d9 6s1. Notice, however, that in each case, the sum of the outer s and d electrons is equal to the group number. This is true for all D block elements within the same group. The D block elements are metals with typical metallic properties and are often referred to as transition metals. They are good conductors of electricity and have high luster. They are typically less reactive than the alkali metals and the alkaline earth metals. Some are so unreactive that they do not easily form compounds, existing in nature as free elements. Palladium, platinum, and gold are among the least reactive of all elements. And we show some D-block elements on the screen here in figure 5-10 or on page 134 of your text. The P-block elements, group 13 through 18. The P-block elements consist of all elements in groups 13 through 18 except helium. Electrons add to a P sublevel only after the S sublevel and the same energy level is filled. Therefore, atoms of all P-block elements contain 2 electrons in the NS sublevel. The P-block elements together with the S-block elements are called the main group elements. For group 13 elements, the added electron enters the NP sublevel, giving a group configuration of NS2, NP1. Atoms of group 14 elements contain 2 electrons in the P sublevel, giving NS2, NP2 for the group configuration. This pattern continues in groups 15 through 18. In group 18, the stable noble gas configurations of NS2, NP6 is reached. The relationships among group numbers and electron configurations for all the groups are summarized in table 5-2, which is found on page 137 or on the screen now. For atoms of the P-block elements, the total number of electrons in the highest occupied level is equal to the group number minus 10. For example, bromine is in group 17. It has 17 minus 10, which is equal to 7 electrons in its highest energy level. Because atoms of P-block elements contain 2 electrons in the NS sublevel, we know that bromine has 5 electrons in its outer P sublevel. The electron configuration of bromine is argon 3d10, 4s2, 4p5. The properties of elements of the P block vary greatly. At its right end, the P block includes the nonmetals, except hydrogen, and helium. All 6 of the metalloids, boron, silicon, germanium, arsenic, antimony, and tellurium, are also in the P block. At the left-hand side and bottom of the block, there are 8 P block metals. The locations of the nonmetals, metalloids, and metals in the P block are shown with distinctive colors on pages 130 and 131, a full color periodic table in your textbook. The elements of group 17, fluorine, chlorine, bromine, iodine, and astatine, are known as the halogens. The halogens are the most reactive of the nonmetals. They react vigorously with most metals to form the type of compound known as salts. As you will see later, the reactivity of halogens is based on the presence of 7 electrons in their outermost energy levels, 1 electron short of the stable noble gas configuration. Fluorine and chlorine are gases at room temperature. Bromine is a reddish liquid, and iodine is a dark purple solid. Astatine is a synthetic element prepared in only very small quantities. Most of its properties are estimated, although it is known to be a solid. The metalloids, or semiconducting elements, fall on both sides of the line separating nonmetals and metals in the P block. They are mostly brittle solids with some properties of metals and some properties of nonmetals. The metalloid elements have electric conductivity intermediate between that of metals, which are good conductors, and nonmetals, which are non-conductors. The metals of the P block are generally harder and denser than the S block alkaline earth metals, but softer and less dense than the D block metals. With the exception of bismuth, these metals are sufficiently reactive to be found in nature only in the form of compounds. Once obtained as free metals, however, they are stable in the presence of air. And let's see. Lastly, the F block elements, lanthanides and actinides. In the periodic table, the F block elements are wedged between groups 3 and 4 in the 6th and 7th periods. Their position reflects the fact that they involve the filling of the 4F sublevel. With 7 4F orbitals to be filled with 2 electrons each, there are a total of 14 F block elements between lanthanum and hafnium in the 6th period. The lanthanides are shiny metals similar in reactivity to the group 2 alkaline earth metals. There are also 14 F block elements, the actinides, between actinium and element 104, which is in the 7th period. In these elements, the 5F sublevel is being filled with 14 electrons. The actinides are all radioactive. The first 4 actinides, thorium through neptunium, have been found naturally on Earth. The remaining actinides are known only as laboratory-made elements. Hopefully now you can explain the relationship between electrons in sublevels and the length of each period of the periodic table. Locate and name the 4 blocks of the periodic table and explain the reasons for those names, and then discuss the relationship between group configurations and group numbers, and lastly, describe the locations of the periodic table and the general properties of alkali metals, the alkaline earth metals, the halogens, and noble gases.